Hey guys, in this lecture we're going to learn how to do FDTD simulations. Finite difference because, so instead of taking the derivative of E and the derivative of H plus 1 minus E of Z over delta Z. Time domain because we use time. Two of the four Maxwell's equations that we're actually going to use, and those are the curl equations. So the curl of H is equal to the time derivative of the flux plus J, the current density. So first things first, we're going to learn here 1D FDTD because it's a little bit easier, and doing the 2D and 3D FDTD uses the same concept as 1D, just more work. So we're going to do 1D FDTD. So we're going to assume that our wave propagates in the z-hat direction. Also, we're going to make the E field oscillate in the x direction. This means that our H field needs to oscillate in the y direction, because E cross H is equal to wave vector, which is in the z direction. Because of this, the curl of H becomes the negative derivative of Hy with respect to Z. We can go from flux to electric field by multiplying by epsilon naught. And J, we're actually going to ignore it for now and come back to it later. Now, we can do the same thing for the curl of E, that since we have only Ex, becomes dEx by dZ is equal to negative. Now, if we want the magnetic field, we need to multiply by mu naught, dH by dt. Okay, so we have these two. Now, how can we discretize it for it to work in a program? Well, that's where this comes in, the finite difference algorithm. So negative dHy by dz becomes negative hy of z plus 1/2 minus hy of z minus 1/2 over dz, which is equal to epsilon naught Ex at point z at time t plus 1 minus Ex at point z of time t, all that divided by delta t. Now, we can obviously do the same thing for the curl of E equation. We're just going to ignore that for now. We know we can do it, so it allows us to isolate the variable that's ahead in time. In this case, it's this one. So if we isolate for this one, Ex at point z, t plus 1, then is equal to Ex at point z of t minus 1 over epsilon naught. Now those are all at time t plus 1/2. So now we have our update equation. Now we can do this. So assuming that we know that we have a starting condition of E fields and H fields, our E field at time t plus 1, and then our H field is going to be at time plus 1/2. So, and Z plus 1/2. So here, and here, and here, and here. And then again, our E fields are going to be here. So the way this works is that we use the previous value for the E field along with the two closest values for the H field, and then we say the E field minus the finite difference of the two closest H fields, this guy and this guy. And all these put together are equal to the next E field. We can do this for every point. How big should our dz and dt be? Our ratio of delta z over delta t should be smaller or equal to c, because delta z over delta t is equal to speed, and the maximum speed we can go is the speed of light. Now, just to be safe, delta z over delta t for us is going to be equal to 2c, which means that delta t, put this in pink, so delta t then is equal to delta z over 2c. Delta t times c is equal to delta z over 2. Each time increment, we move at most half of a grid point. because we obviously can't move faster. I can show you guys what happens when we move, when we try to move faster than the speed of light. Trust me, it doesn't work. And that's actually going to be very useful when we get to absorbing boundary conditions. But for now, so we know our update equations. We know our courant condition here. So now we need to put a source in there. So the source for us is just going to be, for now, J. And we can really set that to whatever we want. But we do want it to be at a value of 0 when we start. Now again, we can go through this finite difference equation and say that ex at time t, ex t minus 1 minus delta t over epsilon naught hy at z plus 1/2 minus ht minus 1/2 of z minus 1/2. And this guy here is our source. So we've already calculated in our program this thing here for ex from 2 to nz. If we make this only happen at one grid point, say ex of source, well, we don't want to add it to the whole thing. We just want to add it to one point, ex source. So what we can do is say that ex source, which is in there, is equal to the previously calculated source point plus a source. So, and there you go. That's it. The source can be basically whatever we want. We do kind of want it to start at 0 and increase from there, because otherwise you have a discontinuity source, which has a few problems. We can check it out later. But for now, source is going to be equal to sine of omega, where omega is equal to 2 pi f. And f, I don't remember what f is exactly, but something like, so 810 E12. And that for now can be our source. In the end, ex source is equal to ex of source plus sine of 2 times pi times 810 E12 times t. Perfect. Okay. So now we can try that. As another source that we can have is a Gaussian. To e to the negative 1/2 t minus t over sigma squared. And this is more useful if you just want to look at a single pulse. That'll work a lot better. Now, if you've noticed, the electromagnetic radiation doesn't ever stop. It just bounces back and forth to the end, back to the source. And that's because right now we have a perfect electric conductor, or a perfect magnetic conductor, at the boundaries. Yeah, I'm gonna explain PEC because PMC is the same but for magnetic field, and PEC is so it's basically the same. Just swap electric field for magnetic field if you want to talk about a PMC. PEC, so electric field inside a PEC is always 0. And that's because the conductivity of a perfect electric conductor is infinity. So because the conductivity is infinite inside a perfect electric conductor, the reflected wave is going to be the negative of the incident wave. In other words, EC, E naught reflected is equal to negative of incident. And why is that? Well, we know that in general, the R is equal to 1 minus beta over 1 plus beta of the incident. Now, beta is equal to mu1 v1 over mu2 omega times k 2. Now, K2 is equal to omega square root of epsilon mu over 2 times square root of 1 plus sigma over epsilon omega squared plus 1 to the 1/2. Since sigma is infinite, this one is going to be equal to infinity. Because K2 is equal to infinity, beta is also equal to infinity. Now, because beta is equal to infinity, you can see that here, when beta is equal to infinity is equal to negative epsilon, or electric field incident. So now we know how a perfect electric conductor reflects the electric field. How to fix this? There's a few ways. We're going to start with the absorbing boundary condition. So we know from our courant condition, the speed of light times our delta t is equal to delta z over 2, which means that it takes 2 or delta t to travel 1 delta z. What if we make ex of 1 equal to ex of 2 time steps to go? In other words, ex of 1 is equal to ex of 2 when t is equal to minus 2 delta t. To do that, it's fairly simple. In our code, we can just write ex of 1 is equal to ex, say, previous. Now, ex previous is equal to ex previous, and ex previous is equal to ex of 2. So this is going to take 2 time steps. So then it would be ex of 1 is equal to ex previous, and so on. And then ex of 2 is equal to ex previous. Okay, so we know how to do that. We're going to try it. It's going to work. It's going to be great. Now, okay, so the absorbing boundary conditions work really well if you have free space. If you don't, however, things get a little bit messy and don't work. Say, for example, you're inside a material with a refractive index of 1.33. That means that your speed at which you go through is going to be equal to c over 1.33. So which means that you're not going to have a round number, which means that this can never work. A different method, though, a method that will work if we have n equals 1.33, is periodic boundary conditions. This method basically has E field here be teleported back to here, and then the H field go here. So E of 1 is equal to E of nz, and H of nz is equal to H of 1. Again, E of 1 is never updated through our update equations, and H of nz never updated in our update equations. Now we're going to give this a try. So now I want you guys to notice something, is that Ex is even at the source. So the section here and the section here are the same. Now, on the other hand, Hy is odd. So the section here is a negative of the section here. If we want to create a one-way source, which would be a lot better, what if we split the source into 2 parts over 2, and then add the other part here over 2, which means that this section is going to cancel out with this section, and then this section will add to this section. Well, we're almost there, but there's a problem. Notice that the amplitude of Ex is not equal to the amplitude of Hy. It's actually about 360 times less. If you do Ex over Hy at any point, you'll end up getting something that looks like mu naught over epsilon naught, which is actually equal to roughly 377. Now, let's think for a bit. What unit could that be? Well, we know that Ex is in units of volts per meter, and Hy is in units of amps per meter. Dividing those two, we get units of volts per amps. Now, if you remember, V equals IR. So R is equal to V over I. And R is in units of ohms, which means that volts per amps is ohms. So EX over HY is equal to the square root of mu naught over epsilon naught is 377 ohms. That is called the impedance of free space. Now, so we know that EX over HY is equal to 377. Our source right now is in volts. We know that I is equal to V over R, which is equal to source over 377 ohms. So to make all of this work, we're going to have to do the source over 2 over eta naught. Now this will give us a one-way source. Let's try it. If we want to if we want to put a material with a refractive index, say n equals 2, what can we change in our code to let us do that? Well, it's pretty simple, really. Is to add epsilon relative from 1 to the distance and mu relative from 1 to the distance. Now, when you go through your code, all you have to do is whenever you see epsilon naught or mu naught, you replace by epsilon r times epsilon naught and mu naught. You're good. That's it. That's all you have to do. Now, coming back to our question, what if we want to add a n equals 2 material? Well, n is equal to the square root of mu r epsilon r. Now, most of the time, mu r is always 1.0. Most materials have a set permeability, which means that it is n is equal to the square root of ER. ER is equal to n squared, which is equal to, in this case, 4. So if you want a material with a refractive index of 2, you just have to set your relative permittivity to 4. And that's it. You're done. You're good. So we're almost there, guys. All we need now is to add conductivity in order to decrease the energy of the electromagnetic wave inside a material. So conductivity works by applying a current density. So we know that current density is equal to sigma E times the electric field. Okay, keeping with our assumption of plane waves and the E field oscillating in the X direction, the H field oscillating in the Y direction, so we can go through and take the finite difference of this equation. So now we have the finite difference for the first part of our equation. Now, the second part, for the J part, what should we do? Well, we know that we have access to EX, so EX at point Z of t minus 1/2, and we will have access to EX at point Z at time t plus 1/2 in the future. Now we can use that, and basically we're going to take the average of the two and multiply it by the conductivity, and that'll give us J. So let's do that. Okay, so we have that. So now we get our final updated equation. Sigma E over 2 times E at time t plus 1/2 of Z plus E at time t minus 1/2 at point Z. Now, if we expand this whole thing, we get the following updated equation. Okay, so that's good. Now, what we want to do is try and factor out this and this. So if we do that, we'll end up getting something that looks like this. I won't go through the whole derivation. It's trivial enough, and I'll let you guys do it on your own. So eventually, you'll end up with this equation here. Now notice how there are two factors, this guy and this guy, that weren't there before. So we can make those be the E factors, E factor 1 and E factor 2. And then isolate for this guy. Because that's our future value. That's what we want. So doing that whole thing, isolating for e of t plus 1/2, you get this. And that is our final updated equation to include losses. Now, obviously, you're going to need to add another array to your FDTD code called sigma. I called it sigma e. So in free space, sigma e is 0 because free space is not conductive. However, for our material, we can set it equal to anything. Okay, so now for our material, so sigma e of left edge to sigma e at right edge, then it's going to be equal to something. Let's make that equal to 5e to the 4. Now we're going to experience some losses within our material. Because before, with only a change in relative epsilon, we had no losses. It was just with shorter wavelength and reflection. Now there's going to be reflection, there's going to be a shorter wavelength, and there's going to be losses inside of material. Hooray!